Hi, in the last session, we understand the idea that how we are going to design Baud Clock Generator in VHDL for our UART project, which is using RS-232 protocol. So today we will write a VHDL code for this, and then we will simulate it with VHDL test benches. So quick brief, this is the block diagram of Baud Clock Generator. We will use 50 megahertz of clock frequency, and we will generate the baud pulses at the baud rate of 115200. We will have this start signal to trigger this baud clock generator. And once start signal is asserted, then this baud clock generator will generate a fixed number of pulses at this baud clock output. And then it will go to the ideal state. We have explained this block diagram in complete details in our last session. So this is just an overview. If you want to understand what we are designing and how this block diagram is working, then please watch my last session. It is really important to understand the logic first. Okay, so let's write the VHDL code for this module. Okay, so first what we will do, we will open VHDL editor, but this time I will use Notepad++ to code my VHDL program. But you can use any VHDL editor which you want to use, okay? So you can see that I have opened this Notepad++ here, and we will write our VHDL program in this editor today. So first we will save this file. So go to this File tab and click on Save As. Now I want to create a new project for this. So I will select some folder from here and I will create a new folder. Now I will give it some name. For example, this is UART project. Okay, so UART project. Now click enter. And this module is our Baud Clock Generator. Okay, so give it some name. Suppose I want to give it name Baud Clock Generator. Okay, because this is our Baud Clock Generator project, right? Now I want to save this file as a .vsd file. So I will click on Save As Type. Now I will search for basic file. So this is VHSIC file. So this is the basic hardware description language. Now I will select this and then click on Save. Now we will write our VHDL program here. So we will start from the library declaration. So give it library IEEE use IEEE dot std underscore logic underscore 1164 dot all. So you can see the benefit of saving this file as .vsd file, because you can see that all the keywords are highlighted with different colors, right? So if you don't save this file as in .vsd, then it will be look like a plain text. Let me zoom in this window so that you can see it very clearly. So this is our library declaration. Now the next is entity declaration. So write it entity Baud Clock Generator is now port declaration. So port, first we will declare the mandatory signals, and these are clock and reset. So clock, that is input type std underscore logic. Next is reset. So reset, that is in std underscore logic. So these two signals are very common signal for a registered process block. Now we will declare the other important ports for this module. So if you remember from our last session, we explained that we are needing three signals for this module. And these signals are start signal, baud clock signal, and ready signal. And all these signals are std logic type. So declare them. So first we have this start signal, and this is input type and std underscore logic data type. Okay. Next we have output port. So that is baud clock, and that is out std underscore logic. And we have one more output, and that is ready. So that is out again std underscore logic. Now bracket closed because all the ports are declared. And finally and entity. So and Baud Clock Generator, right? So this is our entity declaration. Next, we will define our architecture for this module. So first we will write the architecture body. So write it architecture behave of this Baud Clock Generator is, now begin, and in the last and behave or and architecture. So this is the structure of architecture. And we have two sections here. So this section is for declaration. And this section after begin keyword is for your functional design, right? Now what we will do that we will write our VHDL program first and then we will define the necessary signals and constant later. So this is my preferred way of designing. Although you can declare the signals or constant first and then write your VHDL program. But it is really difficult to think of all the signals required for your VHDL programs in the starting of your VHDL code. So first we will write our VHDL code and then in the last we will declare all the signals and constant needed for this project, right? So let's start our VHDL program. So very first we will define this baud clock output because this is our main output of this module and we will write a process to define this baud clock output. Okay. So this is our baud clock output here. Okay. And we are writing this process for this signal. Okay. Now start our process block. So first give it some name. For example, I'm giving this bit period process. This is a process and clock and reset is in the sensitivity list because this is a register process block. Now begin and end process. So this is a basic structure of a process block in VHDL. Now let's write the template for a register process block. So this is if reset is equals to 1, then do something. Else if at rising edge of clock, then do something, and in the last and if. So this is the basic template of a registered process block. Now first we will write what will happen at the rising edge of clock. So we will write a program here in this section. Now in the last session, we have explained that how this baud clock output is generated and how we control the timings of this baud clock signal output. So as we explained, we will use a simple counter and we will count it at every rising edge of our system clock. And when this counter reaches to some specific point based on your selected baud rate, then it will give you the baud clock pulse and your counter will start counting from 0 again, right? So we will write the code for this logic. Suppose our counter name is bit period counter. Okay, so write it bit period counter. So that should be bit period counter plus 1, right? So this statement will increase the counter by 1 at every rising edge of your clock. Now we will define that when this increment will happen. So when it will happen if this bit period counter is less than some specific value, or you can say is equal to some specific value. For example, this specific value is 1000 or 2000, right? But as we said that RS-232 protocol only supports very specific baud rate. You cannot select any bit rate of your choices. So you have to stick on the RS-232 protocol standards, right? And this protocol supports few of the different baud rates. And I want to write a general VHDL code that can be used at any baud rate. Now I do not want to write a very specific VHDL code which can only work with a very specific system clock frequency and very specific baud rate. Instead, I want this code to run on any system clock frequency and any baud rate. So we will not hard code this value here. Instead, we will use the mathematical calculations. And for that, we will use a constant. So instead of this hard coded value here, we will use a constant. And suppose the constant is bit period. Don't worry because we will define all the signals and constant once we finish the architecture part of this VHDL code, right? So if bit period counter is equals to bit period, then what will happen? Then our counter should reset to 0, right? So this bit period counter should be 0, right? Else what will happen? Else we will increase our counter at every rising edge, right? So this is correct. Now let's terminate this if condition as well. So and if, now we will drive this baud clock output within this process, right? So what will happen that every time this bit period counter match with this bit period that we will define, then we want to give a pulse to this output, right? Giving a pulse means for one clock cycle, the value of this baud clock is 1, and for rest of the time, the output will be 0, right? So write it. So if bit period counter is equals to bit period, then our baud clock output will be 1, right? Else, what will happen? Our baud clock output will be 0. Okay. So this process it looks good and it is driving this baud clock output. Okay. Now let's give the reset condition as well, that what will happen when the reset is asserted. So our baud clock output will be 0, right? And our bit period counter will be 0 as well. Okay. So it's covered the reset condition as well. So this process looks good for this baud clock output. And now we will create another process to define that when this baud clock output will generate. Why? Because we want that this baud clock will only generate the pulses when there are some data to transfer. And for rest of the time, it will not generate any data or any pulses, right? So if we leave this process as it is, then it will continuously generate the baud clock output. And we do not want this. We want to control that when we give the start pulse to our this baud clock generator, then only it will generate the number of pulses. For example, if we want to transfer 8 bits, then it will generate 8 pulses. If we want to transfer 10 bits in total, for example, start bit, data bits, parity bit, or stop bits, then it will generate 10 bits. So we will write one another process to control this part of our module. Okay. So first we will give some name to this process block. Suppose this process is pulse control process. Okay. You can give any name, doesn't matter. And this is optional as well. So if you do not want to give any name to any of your process, then you can leave it as well. But if you're using many processes in your VHDL code, then it is always a good practice to name your process block so that you can know that this process is for what purpose, right? For example, our last process was for the baud clock output and we were generating the baud pulses based on our bit period counter. So we gave the relative name to that process, that is bit period process. Now this is pulse control process. So first we will write the basic template of a registered process block. So this is a process. Now clock and reset in the sensitivity list. Now begin and process. Next, if reset is equals to 1, then do something. Else if rising edge of clock, then do something, and in the last and if, right? So this is our basic template. Now what will happen that, so we have this start as an input port here. So when this start pulse is given, our baud clock generator will generate the number of pulses, right? So we need to define that how many pulses we need to give in. And that is depend on the data width, right? So what I will write that if this start signal is equals to 1 means when this start pulse is given, then what will happen? We will load the number of data bits to some internal signal. Suppose this internal signal is pulse pending. Okay, so number of pulses pending. So this is pulse pending that should be equal to your number of data bits. Suppose I want to give it some name, for example, data width. Now, because this data width can be different for your different projects or for your different requirements, because in RS-232 protocol, you can supply flexible number of bits. For example, 6 number of data bits or 7 number of data bits or 8 number of data bits. So it is totally depends on your project needs. So I will not hard code this. Instead, I will use a generic where we will define the data width of our signal. And then I can use this program for 8-bit data, for 6-bit data, or 7-bit data, etc. So always try to write a generic programs for your VHDL designs. So what I will do that I will define a generic for this data width, but I will do it little later. First, let's finish this VHDL program. So pulse banding gets a value of data width, and that will happen when start pulse is given, right? For example, consider the total data width is 10 bits. So we have to generate 8 pulses in the baud clock output, right? Means when one baud clock signal is generated, then your pulse banding will be reduced by 1, right? Like when you give in this start pulse, then this pulse banding will be 10 because the data width is 10, right? Now when your first pulse is generated, then this pulse banding will be 9. And then when your second pulse is generated, then this pulse banding will be 8. And that will happen until 10 pulses are generated at the output. Means at the output of baud clock port, right? So simply write it. If start equals to 1, then your pulse banding signal will match with the data width. Else if when your baud clock pulse is generated, means when your baud clock is generated, means this baud clock is equals to 1, then what will happen? This pulse banding will be pulse banding minus 1. So pulse banding minus 1. Okay. And now and if. So what we have defined in this process block, we are saying that when this start pulse is given, then your pulse banding signal will be matched with the data width. For example, if your data width is 10, then your pulse banding will be 10 as well. When you give this start pulse, right? And when this baud clock pulse is generated, then what will happen? Then your pulse banding will be pulse banding minus 1. But still, we are generating these baud clock pulses in an infinite loop. And we do not want this. We want to generate a very fixed number of baud clock pulses when this start pulse is given, right? So we will write another logic here. And the logic is simply within this if condition. So what I will do that I will run these statements inside another if condition. So write it. So first move it little. So tab. Now give another condition that if this pulse banding signal is greater than 0, then only this baud clock signals will be generated. And when this is not happening, means when pulse banding is 0, then let's move it here. So when this pulse banding is 0, then what will happen? This baud clock will be 0 and this bit period counter will also 0, right? Now and if. So now this process will only generate a fixed number of process, and that will depend on your data bit. And this second process will tell that when these baud clock pulses will be generated for your baud clock generator. One more thing that we have not given the reset condition here, so we will give it as well. So what we'll have when this reset signal is asserted, so if reset is equals to 1, then what will happen? This pulse banding will be 0. Okay. So this is the only statement that we want in this process block for the reset condition. So this process block is also looks good now. Now, if you remember that we have one extra signal that is ready, and this is a output port. And we need to define the functioning for this ready signal as well. And for this, we will write one another process block. Okay. And again, this will be a registered process block. So first give it some name. For example, this is ready output signal, output process. And this is a process with clock and reset in the sensitivity list, then begin and in the last and process. Okay. Now because this is a register process block, so we will write the basic template for it. So this is if reset is equals to 1, then do something. Else if at rising edge of clock, then do something, and in the last and if. Okay. So first we will give the reset condition. So when reset is equals to 1, then our ready output will be 0. Okay, so this ready gets the value of 0. Now at the rising edge of clock, so first understand that what this ready signal will do. So it will tell your UART transmitter that when it is ready to transmit any data, right? This means that when your Baud clock pulses are generating, at that time your UART transmitter is not ready to get any new data, right? Means this ready signal will be logical low. And when all the bits are transmitted and your Baud clock generator is not generating any new pulses, this means your UART transmitter is ready to take the new data. So that's what this ready signal is doing. So basically, this is the indicator that when your UART transmitter is ready to capture any new data. So this is very simple that if start is equals to 1, means when you give the start pulse to your UART transmitter, then your UART transmitter will be busy in transmitting those data signals, right? So if start equals to 1, then this ready output will be 0, means now it is not ready to capture any data at this point of time. Else if, now we will write the condition that when this ready output will be logical high, means your UART transmitter is ready to capture new data. So I will say that when this pulse pending is equals to 0, means all the pulses are generated, then ready output will be high. Okay, now and if. So this process is very simple. When reset is applied, then the ready signal will be 0. Else, when you give the start pulse, then your ready signal will be 0 or logical low. Means your UART transmitter is busy in transmitting the data. And when all the bits are transmitted and your UART transmitter is ready to capture any new data, at that time your ready will be 1. Okay. So our architecture part is also completed. Now let's zoom out little, and it's the time when we need to declare all the signals and constant which we have used in this architecture section. Okay. So let's define them. So we will declare all the signals and constant in this section of architecture. Okay. But before this signals or constant declaration, let's define our generic that we have used in this process block here, and that is data width, right? Which is defining our number of data bits, right? As I said, we will define this as a generic. So let's copy this data width, copy, and let's define a generic for this data width. So we define the generics here in this section of entity. So write generic. Now define all the generics in this section here. So we have this data width, and that is integer. And for example, we are giving some initial value of 10. Okay, now we will define this bit period. So this is a constant. So we'll define it here. So this is a constant bit period, that is integer type. I want to initiate this bit period integer with some initial value, right? So this will be like 434. So constant bit period, that is integer type, and it is having the value of 434. Now the question is that how we will define the upper range for this integer. Now for this design, it depends on two factors. Number one is your system clock frequency, and number two is your baud rate. For example, your system clock frequency is 50 megahertz and you are designing the system for a baud rate of 115200. So this upper range will be 50 megahertz or 50 millions, 50, 1, 2, 3, 4, 5, 6, 50 million divided by 115200. So this is our baud rate, right? And the value will be 434. So this constant bit period is an integer type and having the range of 434, right? But instead hard coding this with 434, because now this is very limited to a 50 megahertz system clock frequency and 115200 baud rate. So to make it flexible, what I will do that I will use that same mathematical calculation here. Okay. So what I will do that I will create two more generics. One is system clock frequency. So sys clock frequency, and second is baud rate. And this constant bit period will be system clock frequency divided by baud rate. And now we will define this system clock frequency and baud rate in the generic section. So go to the generic section once again and define these two generics. So this is system clock frequency, that is again integer type, and give it some value. So for example, in our case that is 50 megahertz. So this is 50 million times. And next generic is baud rate. So this is baud rate integer type, and the value is 115200. Okay. This means that now you can use this VHDL program for any system clock frequency and any baud rate and for any data width, right? So this is the benefit of using generics in your VHDL programs. So let's come back to the declaration section or declaration part. So I have defined the constant bit period. Now we will define all the signals which I have used in our VHDL program. So first signal is this bit period counter. So bit period counter. Now this is integer type. Now this is fine if you declare your bit period as an integer like this. But as I said in the best practices session, that you should always define a range with your integer values. And that will help to optimize your FPGA resources. And we will also define the range for this signal. So range from 0 to, so if you notice in this process block here that it is counting from 0 to bit period, means because when this bit period is occurring, we reset the bit period counter to 0. This means that it will only count from 0 to this bit period range. Okay, so define it, signal bit period counter integer range 0 to bit period. Okay, so we have defined this bit period counter here, and let's look for any other signal which we have used. Yeah, so we have used this pulse pending, so we will define this as well. So this is a signal pulse pending, and this is integer type and having the range from 0 to, now if you look at this process block of for this pulse pending, then you will see that this pulse pending having the highest value of data width. And for each baud clock pulses, it is reducing its value by one factor. So this signal pulse pending will be having the range from 0 to this data width. Okay, so this is having the range from 0 to data width, right? Now let's see if any other signal is pending. So this baud clock, so this is output. So we have already defined that in the entity section. This bit period counter, we have defined that as a signal. Then baud clock, again, this is the output port. Period counter, we have defined this. Now pulse pending, we have already defined this again. So everything has been defined. Now this ready, so this is our output port. So we have already declared this in the entity part. And now all the signals are defined for this project. Okay, so this is our VHDL code. Now let's zoom out little so we can see the whole program. Okay, so everything is looking good. Now let's save this program. Now this time I will compile this program in the model sim simulator. So for this, I will open this model sim. Okay, so open this model sim simulator or model sim tool. Okay, let's maximize this. Now first we will create a new project. So I will go to this file tab and now click on new. Now you will see this project section here. So click on this. Yes. Now give some project name. Suppose our project name is UART. Now give the project location. Now suppose I want to save this project in this folder. So I have already created this UART project here. And let's create a new folder here. So click on new folder and give it some name. So this is model sim UART project. Okay. And select this folder. So this will save at this folder location and the project name is UART. Now click on OK. Now it is asking if you want to create a new file or you want to add any existing file. So I will select this add existing file because we have written our VHDL code in Notepad and saved it. So I will browse that file and I will open it. So we have this Baud Clock Generator, that is VHDL file that we have just written. So I will select this and click on open button. Now click on OK. Now, if you have more files to add, you can again click on this add existing file and follow the same process. And once you add all the files, then you can click on this close button. So now you can see that this Baud Clock Generator.vst, this file is listed here. Okay. Now this question mark and the status is because we have not compiled this yet. We have only added this file into this project. So first we will compile this VHDL program for any syntax error. Okay. So you can see this compilation button here. So you can click on it and the compilation will start for this program. Else you can simply select this file, then right click and you will see this compile button here and just click on compile select. Okay. Now, if you have multiple files in the same project, then you can select this compile all option here. But we have this single file at the moment. So I will select it and then click on compile selected. Okay. Okay. So you can see the compilation has given us some error. Now I will click on this. So it will tell that what is the problem. Okay. Now I will double click on it. So it will land me on the problem. So it is saying that there is some problem at this line here. Yeah, that's right. Because when you define the last generic in this section, then the semicolon at the end after closing the bracket. So this follows the same syntax as the port declaration, right? So I will save it again. Let's save it and then right click, compile and compile selected. Okay, now this more error. Now let's see what it is saying. Okay, double click on it. Okay. So this Baud clock, that is an output and this is std logic data type, right? So I have to use single quotes to write any value for std logic. Now save this. Let's compile it again. Compile, select it. Okay. So number of errors are reduced now. Okay. Now what it is saying. So it is saying that at line 60, I have used this Baud clock to check for any condition. Means we have used this Baud clock signal to read data from it. But this Baud signal is actually an output signal. And this error has come because VHDL does not support this. This means that you cannot read any signal in your VHDL program which is declared as an output port. And here we have declared this Baud clock as an output. So that was not allowed in the previous version of VHDL compilers. But if you are using the recent VHDL compiler, then it is supported. So you can see that it is also listed that this is the error, that you are using this Baud clock as an output port, but at the same time you are reading this output signal. And this is not allowed in the previous VHDL compilers, but that is supported by VHDL 2008. Okay, so I will close this. So I will update the VHDL compiler for this project. So for this, I will select this file. Now click on properties and here I will select this VHDL and select this 2008 version and that's it. Click on OK. Now again we will compile it again. So compile, compile selected and you can see that error has been gone. So this is compile of Baud clock generator was successful. So this means that our Baud clock generator is successfully compiled and it is free from any syntax error. But that does not mean that this program is logically correct, right? So to test the functionality of our program, we will simulate this module in the waveform. And for that, we will write a test bench in a next section. And then we will simulate our program in the terms of waveforms. And we will see that if this program is working fine logically or not. So that is one module of our UART transmitter. And before using this module in the UART transmitter, we will test this module. So in the next session, we will write a test bench for this module in VHDL. And then we will see the simulation results as well. So stay tuned for the updates. If you did not subscribe till now, then please do subscribe to learn and grow community for regular updates. If this video is informative, then please like this video, comment on video, and don't forget to share. Thank you for watching.